Hi there, this is Lucius Laframboise from QESuite, and today we're going to talk about the normal distribution and what is normality. To start, we're really going to talk about what it means to be an engineer. And engineer comes from the fact that we use the engineering method. The engineering method is the use of heuristics to cause the best change in a poorly understood situation within the available resources. So you'll notice that the word heuristics is in bold here because that is really the key term when it comes to understanding engineering. Heuristics are an approach to problem solving that employ practical methods that aren't guaranteed to be optimal, perfect, or rational. So they're not necessarily going to be the best, but it's sufficient for reaching the goal or approximation. That kind of goes back into the other one where it says the best change. We are just trying to make the best change possible, right? Another important thing to understand about engineering is the fact that everything we do is based off of assumptions. Since we're using heuristics, these are kind of like rule of thumb, right? It's a rule of thumb. That rule of thumb can only be used if certain things can be assumed. So those would be your assumptions, the baseline truths that a heuristic relies on. Any assumption required by a heuristic is not appropriate for the scenario. So if in order to use the heuristic, you have to be able to assume the sky is blue and it's not appropriate for the scenario because it's overcast, then the heuristic cannot be deemed sufficient for reaching the goal or approximation. So the reason we're talking about this to start our talk about normality is because normality is an incredibly important assumption in many different engineering statistics. The problem is we can only ever assume normality. We can never prove it unless the data is generated from a normal density function. If it's not actually generated from a density function, we cannot ever do more than assume. And how do we know that that assumption is valid? Well, that's when we use normality tests. Normality tests are hypothesis tests that allow us to either reject or fail to reject the null hypothesis based on a critical value or a comparison to a p-value, right? So what is the normal distribution? We know it's important to know whether or not our data can be assumed to follow the distribution, but what is the normal distribution? The normal distribution is sometimes called a bell curve or a Gaussian distribution, and there are two main distributions that we care about regarding the normal distribution. The PDF, the probability density function, so that's the PDF is 1 over the standard deviation times the square root of 2 pi times the exponent of negative 1/2 times x minus mu over sigma squared. Okay, what does that even mean? Well, PDF, your probability, f of x, is the probability of a value x occurring given the standard deviation and mean. Okay, so that's this graph over here. As you can see, at 0 standard deviations away from the mean, so the mean, we have the highest probability of getting a value that is the mean. And as we step away from the mean, it curves down and our probability gets lower. So a lot of times you'll hear about 6 sigma and a 6 sigma spread. That's because everything between -3 and +3 standard deviations away, so 6 sigma, is more than 99%. So that comes out to, I think, 30 parts per million failing if you're within that 6 sigma. Okay, so that's where it comes from. It actually comes from the normal distribution, which is kind of cool. The other one that you're going to care about, and this one is really more important. The probability density function makes more sense, where I can actually say, well, the probability of me pulling this number out of the distribution is this %. Cumulative distribution function is a little less intuitive. And what it is it's actually the integral. So if you were to integrate your probability density function, you would get your cumulative distribution function. So if you know anything about integration, what integration does is it's actually adding the area, it's taking the sum of the area underneath whatever function you're integrating. So what that means is, in this case, if we're adding up, like let's say we want to get this cumulative distribution function at the mean. So we know that the probability is going to be a little under 40%. Okay? If we were to integrate it, what we're actually doing is adding up the probability of getting every single value less than or equal to the mean. So that means the cumulative distribution function, f of x, is actually, if you were to plug in x, it's telling you the probability of you getting a value less than or equal to that value, okay? That value of x. And the formula for that is 1/2 times 1 plus the Gaussian error function of x minus mu over sigma square root 2, where mu is the mean and sigma is the standard deviation again. Okay, the error function is not something you could ever do by hand. It's something that computers have to approximate. So don't worry about that. Use Excel or use some other software to get that. But just know that in this case, this is what we're going to use most in engineering. And there's some really cool things we can do with them, such as capability like a PPK. If you haven't seen that video, I highly recommend it. It's a real-life application of a cumulative distribution function for the normal distribution. Okay, so now we know what the normal distribution is and what the probability density function and the cumulative distribution function are. But why are they important? Well, the normal distribution is really important for two reasons. The first being the central limit theorem. Using some math, you can show that after 30 samples, the variance will level out. So that means the difference between 30 samples and 30 million samples, you shouldn't see a difference in the distribution fit. And there's some really excellent math. I highly recommend you looking at that if you're interested into it. Maybe we'll take that on someday, but we won't today. So why does that matter for engineers? Well, as engineers, we're trying to use the best solution with the available resources. We don't have the available resources to test an infinite number of samples. The goal of engineering is to test as few samples as possible and get a valid and reliable representation of our population. So if we can assume normality, then we can assume that after 30 samples, our variance should level out to a negligible point where we only need 30 samples. Okay? The second main reason is capability, because capability assumes normality, and capability really is the measure of whether or not your product can produce parts that are in spec. And again, that goes back to your cumulative distribution and actually being able to calculate the expected probability of a failing part. It's some really cool math. I highly recommend you check out that capability video right here. That goes into the math of how to calculate that. Kind of a cool one. If we want to be able to assume normality, we have to be able to test whether or not that is a valid assumption for the scenario, for our data. And in order to do that, we have a few different tests. We have the Anderson-Darling, the Ryan-Joyner, the Kolmogorov-Smirnov, and the Jark-Barrett test. So there are many more tests, but these are the four that are in QESuite. They're four very common ones, and they all have a slightly different method of testing that makes them useful in different scenarios. So we'll get into those later. Each week we'll take on a new one, and we'll dive in depth, and I'll actually show you the math of how to calculate it. So moving away from testing normality, we're going to talk a little bit about two descriptive statistics that can be important when understanding your not so normal distribution. The reason I say not so normal is, let's say you pass normality, but it looks a little weird. That generally means that you have a skewness or kurtosis that are not equal to 0. So first, let's talk about skewness. Skewness is a measure of the asymmetry of a distribution. So it's really a descriptive statistic that helps describe the shape of the distribution. So if you were to draw a line connecting all of your data, and it's sorted from smallest to largest, you're going to be able to see skewness of 0. That means that the data is symmetrical. So that's like your normal distribution, very, very symmetrical. Skewness of less than 0, so a negative skewness, the left tail is going to be longer. and then a skewness that's above 0, a positive skewness, the right tail will be longer. So what does that mean? Left tail, right tail. Well, to figure that out, we'll have to actually take a look at two distributions with different skewnesses. So on the left, you'll see a negative skew, and on the right, you'll see this positive skew. So on the left here, you'll notice that the left tail is longer. So it kind of looks like the distribution itself is going to tip over because there's just so much slope on this side, and then there's so much slope on this side. The left tail is this, and the right tail is this. So you'll notice here on this negative skew where the left tail is longer, it looks like if you were to slide down there, you would be on the slide for a really long time because it's a lot longer. Whereas if you were to slide down the right, it would be pretty short. It's a very short slide. So in the case of a positive skew, the right tail is longer. One way to think of it, again, is the slide. If you sit and you were to slide, you would slide for a really long time. If you were to sit and slide down the left tail, you would slide only for a little bit. So those are your tails. It's just which side of the mean you're on, and a negative skew would be a longer left tail, a positive skew, a longer right tail. So that other statistic I mentioned is kurtosis. And kurtosis is a measure of tailedness. So that's how heavy are your tails. Kurtosis is another descriptive statistic that describes the shape of the distribution. So down here, you'll see again, your normal distribution has a 0 kurtosis. That's your Gaussian distribution. So it's just a regular normal curve, a normal curve, right? A positive kurtosis would mean that it looks kind of skinny, almost like you have a really small standard deviation, right? And then a negative kurtosis, it's very flat, kind of more rounded, not as sharp. It means your tails are much heavier. So kind of like with skewness, this has a lot to do with the tails of your distribution. In the case of a positive kurtosis, you don't have much tails at all. Everything is really stacked right on the mean. Whereas in a negative kurtosis, you're very heavy in the tails. And you can have skewness, a positive skew, and a negative kurtosis. Those aren't related. They just kind of describe two different things, where skewness is the direction of your tail, and kurtosis is the weight of your tails. So the normal distribution is symmetrical. It has a skewness of 0, and kurtosis is actually standardized on the normal distribution. So k equals 0. We can use tests like the Jark-Barra test, which is included in QESuite, that compares the skewness and kurtosis of your data with the expected values, which are just 0 and 0. So it's just another way of testing for normality. This one is going to be a lot less selective because when it comes to like an Anderson-Darling, it's going to put a lot of weight on whether or not your probability distribution is lining up, the probability of actually getting those values. Whereas your Jark-Barra test, which is equally useful in certain cases, really just says, if we were to overlay these graphs, does it look close enough to the normal distribution? But it gives you a number that quantifies how close it looks, right? And as we go into normality tests, I'll kind of explain what each of them is really good for and why we might use certain ones instead of others first. All right, so to conclude this video, I just wanted to go over some main points. The normal distribution is a really important distribution in engineering for 3 main reasons now that we've learned a little more. The first, many other tests and statistics assume that normality. Capability, again, very important. 2, the central limit theorem proves reliability and validity for smaller sample sizes. That's that n equals 30 thing. And then the third one, this one we didn't touch on yet, but it's kind of an interesting one to know. A normal distribution is the expected distribution for most types of engineering measurement sets, because it's common for random continuous variables that represent magnitudes with no minimum. Okay, that is some crazy wording. What does it mean? Well, a random continuous variable is a variable that is random, so it can be anywhere. And then continuous means that it's not like in 1, 2, 3 on, off, it has, let's say, a continuum. And it could be 1, 2, 3, I guess, if it's a number line that, you only have precision down to 1, 2, 3. But let's say maybe instead of 1, 2, 3, it's 3 people's names, right? Or 1, 2, 3 are names instead of numbers, right? So it's really common if you have, like, let's say you're measuring the length of something or the height of people. Magnitudes, it's about something that has a size to it. If you remember from a physics lesson, magnitude is the actual size of something. And it doesn't have to just be size, but it is really on something where it can kind of be bigger or smaller. And there's no minimum. If you have something like, let's say you're so close to 0 that you can't go down to 0, then you might not hit the normal distribution, because let's say you're making something at like 10 thousandths of an inch. It's a hole that's 10 thousandths of an inch, and you're plus or minus 15 thousandths. Well, now you have a minimum, and you might be cutting off the distribution. So that's why it's important. In almost all engineering scenarios, you would expect a normal distribution. Thanks so much for watching. Have a great day, and please do something awesome.